The tri in TRIzol comes because it actually allows you to extract 3 different things: RNA, DNA, and protein. We're most often typically using it to extract RNA, such as from cell samples, because it's going to help you break the cells open, lyse them as well. But once you remove the RNA, then you can still go back and get out that DNA and that protein. With all of these, the basic idea is the same. You're going to give these molecules a choice of where they want to hang out. They can hang out with the watery stuff, or they could hang out with the organic stuff, the stuff that's like kind of, you can think of it for now as like anti-water. And so normally you think, okay, well, they're going to hang out with the watery stuff. So we have to make changes to them in order to get them to not want to hang out with the water. And so this is where the stuff that's actually in here comes into play. So TRIzol is a brand name, but it's acid guanidinium thiocyanate phenylchloroform. The chloroform part you add later. And so basically it has this it's just like a normal like phenylchloroform extraction, but it has this guanidinium thiocyanate, which is what we call a chiotrope. And so basically it's going to help like break things up, help denature proteins, and this is going to help so that you keep the RNases and other nucleases, so the DNA and RNA chewers, away from those precious samples that you're trying to protect. It also is going to help break cells open. If you're starting from a cell, you can also start from other things, other types of samples, more purified samples and stuff like that. And it's going to denature all the proteins. And so when it denatures the proteins, it unfolds these proteins. Because you're at an acid environment also, now when you're going to selectively precipitate out the DNA, as we'll talk about, and so now the DNA doesn't want to hang out there either. So the RNA is the only one that's going to be stuck in this watery mix. So you can then, when you add the chloroform, that's going to make this layer even more like dense and separate better from the water layer. So you have this like anti-water layer, and you have this water layer. And then the RNA is going to be the water layer, and then other stuff is in the anti-water layer. So now basically what you've done is you've given these molecules a choice of which of these different solvents they want to hang out with, which of these different liquids they want to dissolve in. We'll get much more into the details of some of this terminology. But once they choose, then you can separate those different parts. So you can take the RNA from this aqueous part, you can take the DNA from the interphase, so the kind of part between the phases, as well as from the organic phase, from this like anti-water phase, as well as just that organic phase itself. And then what you can do is you take that watery part, the aqueous part, and you can precipitate out the RNA. So we got these molecules to separate into which ones they like. Now we need to get them to not like them so much. So we need to somehow change this solution, change the liquid, change the solvent, so that now they don't like it anymore. Now there's not another option to go to though, and so their other option is to precipitate out, so to come out of solution, so to bind two copies of themselves instead of to be forming these interactions with the molecules of the liquid that they're surrounded in. And when they precipitate out, then we can centrifuge them, we can spin them down really fast, and all of that stuff that's precipitated out, that's not in solution anymore, is going to collect into a pellet. Once it's in that pellet, well, now we have the ability to wash it, as long as we keep it in the precipitated state. And so we can do washes with things that we'll get rid of, things that we want to get rid of, like salts and that sort of thing. If we do, say, like an 80% ethanol wash, that's going to keep the RNA, which you precipitate out by adding isopropanol, which is going to basically make it so that the salts can interact with the RNA more and neutralize it, so that the water doesn't want to hang out with it and there's nowhere else to go, so the RNA is going to precipitate out. Then when you wash it with like an 80% ethanol solution, now what you're going to do is those little salts are going to be able to dissolve and you can get rid of them, but the RNA, it's all big, it's all gummed together, it's going to take more to dissolve it. And so that's why you can do all these washes while your stuff is still pelleted. And then finally, once all that stuff is away, well, now you can resuspend it, add a liquid back that it likes, and now it can resuspend, and you've got your purified RNA. Okay, well, what about that DNA and the protein? So they were hanging out in those other parts of the stuff that we ignored when we were caring about the RNA, but they're still there, and so we can go back and we can get them out. And we do the same sort of thing, but here we use different strategies. And so we're going to precipitate out the DNA. Instead of with isopropanol, we're going to use ethanol. And this is going to precipitate out the DNA. But the same sort of principles. We do some salt washes, we resuspend it, And then, okay, well, we precipitated out the DNA, so we got it to we got it to go to the one it wanted, then we got it to not want that one, then we got it to resuspend in something it does want. Okay, so we got rid of that. And now the proteins. So the proteins are going to take a little more to precipitate out because they've got like more parts that are going to be happy in the various solvents. But when you add isopropanol and you've diluted out all that other stuff, well, now the proteins aren't going to want to hang out in that phenylchloroform ethanol solution that precipitated out the DNA. So you've gotten rid of the RNA and the DNA, and now you're left with your protein solution. To get the proteins out, well, now you can add isopropanol. The protein's finally like, okay, I'll give in. I don't want to hang out here anymore. I'm going to precipitate out. So the solvent doesn't want to hang out with it. It doesn't want to hang out with the solvent, so it's going to hang out with itself, and the solvent's going to hang out with itself. Your protein's now precipitated, you can do washes, and then you can hopefully resuspend it. So with the protein, it's going to be a lot harder to resuspend. You typically need to use like detergent, like SDS. I'll get in some heat and stuff. Sometimes you dialyze it. I'll get into this stuff. But long story short, you're typically not, this is not your first go-to place if all you care about is that protein. There are easier methods for getting the protein, and you can actually use like just add nucleases or DNA and RNA chewers to chew up the DNA and RNA, isolate the protein without them, without having to do all this fancy extraction. There are also kits that allow you to like take the aqueous phase from this and just like purify them on a column, or even go straight from this without even doing the phase separation with these column-based methods, and so I'll get more into those too. But the basic idea is still the same, where you take that first initial extraction, rely on the acidic nature of the phenol solution. So there's like phenylchloroform solutions. TRIzol is just like a brand name, and with the thioisonate, vanadium thioisonate. But you can also just like make it yourself. I'll link to a recipe. But the key thing is that this phenol solution that we're using is acidic, and this is going to make it, as I'll get into, so that the DNA is not going to hang out in the aqueous phase, but the RNA is, because it's still got that 2'-OH, which is given it enough to be happy with for the water to be happy with it. Okay, so now that we've gone over this, let's step back, go into the details, because yeah, details matter. This whole thing is just going to be a game of solubility, finding small differences between biological molecules like RNA, protein, and DNA, and then kind of like amplifying or accentuating those differences in a way that's going to make it so that they're more or less likely to dissolve in various liquids. And so we call these liquids that they have the choice to dissolve in the solvent, and then the thing that's dissolving is the solute. So I say like they're given a choice. Basically what happens is that in order for something to dissolve, it has to get a full coat of the solvent. This means that the solvent has to give up some of its interactions with other solvent molecules, so these like solvent interactions, and it has to make some of the interactions to the solute. And the solute has to give up some of its interactions to other copies of itself, the solute interactions, to make some interactions with the solvent. So both the solvent and the solute have to kind of like each other enough to let each other into their networks. And because different molecules have different properties, such as different partially charged regions, this is going to come into play a lot, this idea of polarity, how molecules can have partly positive and partly negative parts. This comes into big play when we're talking about aqueous or water-based solutions, because water is highly polar. It has a highly electronegative oxygen, so this is a highly it's going to be an electron hogger. Basically, the hydrogens and the oxygens are connected by sharing pairs of electrons. Electrons are negatively charged, and so since the oxygen is hogging them, the oxygen is going to be partly negatively charged, and the hydrogens are going to be partly positively charged. And this uneven distribution of charge we call polarity, and it makes it so that water is really sticky to itself, as well as sticky to other things with full or partial charges. And it doesn't want to hang out with things that are what we call hydrophobic, so things that don't have charge or partial charge. Those things are going to be excluded from the water network, and they're kind of going to, the water's going to bully up and cinch around it and push them together into an insoluble clump, basically. So whether or not something dissolves is going to depend on basically its chemical makeup. And this chemical makeup, although the core makeup of it, like which atoms are connected how, isn't going to change other than protonation and deprotonation. The various conditions, by changing the solvent, we can change whether or not those
molecules would rather hang out with copies of one another or with copies of the solvent. So our basic idea is that we're going to start with a mix of solvents, let molecules choose their favorite one, take the portion that they choose, change the solvent so that they like it less, wash off stuff while they're still precipitated out, and then add a solvent they like again so that you can redissolve it. So we're going to be starting with a liquid-liquid phase separation, and then we're going to just be pelleting things out. But in our first separation, what we're actually doing is we're giving a choice of solvents. You can go to the aqueous phase or the water-based phase, which is where you started with, or you can go and you can separate out into what we call organic phase. And so organic, we use the word organic to refer to molecules that are based on a hydrocarbon skeleton. So basically hydrogens and carbons, and these have this property where they're very non-polar, at least when it's just hydrocarbons. And so they don't have any of that partial charge or that full charge that makes water want to hang out with them. And so they're going to separate out. You can think of this kind of like an oil and water mixture, maybe one of those salad dressings, where they're not going to mix together, and so they'll separate out into different layers. What happens is that because you don't just have that aqueous phase and that organic phase, you actually have those molecules that are in there. The molecules have a choice. Okay, well, do you want to hang out with the aqueous phase? Do you want to hang out with the water? Do you want to hang out in the organic phase? Do you want to hang out with that phenol or chloroform? Or do you want to, or do you not like either? Would you rather hang out with yourself? In which case you could end up kind of precipitated in this region in between the two phases. We call it interphase, which is this kind of like gunky white layer. So what is in this aqueous and these organic phases? Well, we're using one of these trial reagents. It's made up of chlorinium thiocyanate, which is this salt, and then phenol, which is this alcohol with this aromatic ring. This is the TRIzol. You typically add the TRIzol directly to your aqueous solution. When you do this, then things are going to start to have a choice to go into that TRIzol layer or the aqueous layer. But these two layers are partly like miscible on one another, which means that basically the two liquids can kind of mix. You want to make sure that those liquids are going to totally separate. And so in order to get them to separate better, you add chloroform. So chloroform, this is the molecule chloroform. It's going to help the phenol and water separate. So it's going to make it so that phenol is holding on to less water. And remember, the water is going to have some of the stuff that you want. Specifically, it's going to have the RNA. And so you don't want it stuck in that organic phase. And so the chloroform is going to help the phenol, help the organic phase have less water and also be heavier. What can happen is that this organic phase, it should be sinking to the bottom. But if there's a lot of stuff in the aqueous phase, like maybe you have a ton of RNA or something, well, now maybe it's denser than the organic phase, and you can actually get this phase inversion where these flip. Now that would be really, really troubling, especially if you don't use this like TRIzol that has the dye. So the dye in the TRIzol is it's labeling the organic phase so you can see it better. If you don't have that dye, now they're both kind of similar looking. And if they flip, well, now if you go to take the aqueous phase from the top, but you've had these phases flipped, you could be taking the wrong thing. Chloroform is going to help them separate. It's going to be more dense, and so it's going to make the organic phase more dense because the chloroform is miscible in the phenol, so the chloroform is mixing in this like even so mixture with the phenol, and therefore it's going to sink to the bottom. Another thing you can do to try to make a clearer separation is to use this phase lock gels, which basically is this kind of like vacuum greasy type stuff that will then the organic phase will collect under it, the aqueous phase over it, and it therefore allows you to more easily separate the two. So you get your aqueous phase. This is going to have your RNA. You have your organic phase. This is going to have your proteins and some DNA, and then you have your interphase, which is going to have some DNA. And your organic phase is also going to have some lipids, so some like fatty things. Depending on what your starting material is, you might have a different combination of things. So if you start with, say, some partly pure reaction mixture where you just had RNA and some enzymes that were modifying the RNA, and now you just want to purify out that pure RNA without those proteins. Well, now you're not going to have all the lipids and stuff. But if you were to start with a cell and that you're breaking open, now you're going to have lipids and more crud that you're trying to get rid of. But anyway, the RNA is going to be in this aqueous phase, and you can take off that aqueous phase to isolate the RNA from it. And then the DNA and the protein are going to be left over. Your next step there is going to be to precipitate out the DNA, take the liquid that's left over, and precipitate out the proteins. So you can selectively precipitate out these various components. And then once they're precipitated out, then you can wash them under conditions where they stay insoluble. And so when they stay in that precipitate, in that clump, then you can use a liquid that's going to dissolve things like maybe the salts that you want to get rid of, but they're not going to be able to dissolve the molecules that you're trying to purify. And then finally, once you've had all that stuff washed off, now you can redissolve things. And so in order to get this selective precipitation and dissolving and separation, we need to kind of play around with what the different molecules like under which conditions. So how do we get the RNA to separate out? This is going to take advantage of what might seem like a really minor difference between DNA and RNA, but it makes a big difference. And this is this 2' OH. So the D in DNA is for deoxy because it's deoxyribonucleotides. It's missing this 2' hydroxyl group. Might not seem like that big of a deal, but this is one of those molecules that we say is polar. Because remember, the oxygen is really electronegative. It's going to pull the electron density, making the oxygen partly negative. And it's also going to allow it to form these things called hydrogen bonds, which are just a special type of partial charge attraction. Now, the rest of it is really similar. It's got this negatively charged backbone, and this negatively charged backbone is normally going to make it really attractive to water because water, remember, has those partial positive hydrogens. And so normally, if we were to take a mixture of DNA and RNA and proteins, as long as we're talking about like just typical water-soluble proteins like you find in the interior of your cells or hanging out outside your cells, but not in the membranes, these are going to want to hang out. If you give them an option of hanging out with the aqueous phase or the organic phase, they're going to hang out with the aqueous phase because, I mean, that's what they're like designed for. That's where they're used to. So we need to change them in a way that's going to make it so that they no longer want to hang out there. And how are we going to do this? Well, how we do this in terms of the DNA and the proteins, but keeping the RNA soluble. And the way that we can do this is by lowering the pH and adding a high amount of salt. Now, what's going to happen here is that at this low pH, you can selectively remove the DNA and keep the RNA soluble. This is because that you have a couple things going on. One is that normally this backbone is going to be surrounded by water molecules. This is like a solvents layer, we say. And this solvent layer is going to kind of shield the nucleic acids, to shield the DNA and the RNA from actually coming into contact with other things and from seeing those other things. Kind of like it's making things foggy. The water, remember, it's really polar. It really likes to stick to itself. And so it's going to form these exclusive networks. If we add a chiotrope, it's just one of the words we call, this means like disruptor. But basically, it disrupts the water networks and it kind of loosens them up. And it has the salt ions, which is going to make it easier for the salt. So the salt is going to loosen up the water molecules and make it easier for these salt ions to find the backbone. And so when we have a cation, a positively charged molecule, it can then bind to the negative charge region and help neutralize it. Also, so in this TRIzol, there's typically like sodium citrate. Well, there's proprietary things, but like the make it yourself recipes typically have sodium citrate, which is another salt that can help with this. So the cations can bind to and bind to that backbone, but that's for RNA and DNA. So how are we getting differences with RNA? Well, what happens is that at the low pH, these bases start to pick up protons. So sometimes you might see that these backbone groups are going to take up the protons, but these groups are going to have like a super duper massively low pKa. So it's more likely, which means that you have to get to a really, really low pH, so where there's a lot of proteins in order for them to protonate. But the bases can take up protons more easily. And when you have the DNA bases take up protons, well, now it's going to disrupt the interstrand binding so that the strands can like come apart or denature. It's going to help like destabilize the DNA. And because you don't have that 2' OH, it's going to make it less soluble than the RNA. And so the DNA is going to precipitate out and or go to that, so it can be in like the interface, or it can go and hang out with that organic phase, but the RNA is going to stay soluble in the liquid phase because it still has that 2' OH, which is providing enough polarity in order to keep it water soluble. But what's going to happen is that when you add isopropanol, you can precipitate out the RNA. How this works is that when the isopropanol, it's going to, so you take the aqueous phase once you separated these. The aqueous phase is going to have your RNA. When you add isopropanol, well, now that RNA is going to no longer be dissolving. Here, you're not giving it a choice of solvents. You're just saying, okay, you're in this solvent. When you add the isopropanol, it's going to mix with this aqueous phase that's already there. It's not like you're forming separate layers. We're not doing a phase-phase separation. We're just doing a precipitation. And so RNA has the option of, okay, you can hang out in this aqueous plus isopropanol mixture, or you can precipitate out. RNA ends up precipitating out because what's going to happen is that the isopropanol, it's going to have a lower what we call dielectric constant, which is this kind of scary sounding word. But really, it just means that it's going to make it easier for the salts to find the RNA backbone and hide its charge like we talked about. So when you think about the salts and the RNA backbone, they're going to want to come into contact with one another. But what happens is that if the water is like surrounding them in that tight shell that we talked about, it's going to be really hard to find them. And so when you add something like an alcohol, like isopropanol, what it's going to do is it's going to kind of reduce the amount of water. So you can think of you're adding more stuff, and so there's going to be less water effectively. And because this isopropanol is less polar, well, now what's going to happen is that there's less stuff kind of stuck to the RNA, and there's less of this shielding in between the RNA and the salts. So there's less like water hiding things. It's kind of like if you had two magnets. If you have a high dielectric constant, it's like having a bunch of sheets of paper in between those magnets. So it's harder to see everything. But if you have a lower dielectric constant, it's like you have less pieces of paper, and so the magnets start to feel each other more. When the salts and the RNA backbone can find one another, well, now they can come together. Now they can neutralize. Remember, water doesn't like neutral things, and so it's going to precipitate out. To aid in the precipitation, we often add a molecule like the lycopene blue, or some other co-precipitant or precipitating agent, which is going to kind of add bulk, make it easier to separate out the RNA. And the glyco blue is nice because it has this blue dye, so it's going to make it easy to visualize. Once it's precipitated out, then you can remove that liquid, so you can like aspirate it off. So they just suck it off with like a pipette very carefully, so you're not disrupting that pellet. More on this in other posts. And now you can do washes. So now you've taken advantage of the fact that not only did you separate it from the DNA and the proteins, well, now you've been able to take off the liquid that it was in, and you have the chance to take off anything that you don't want, anything. as long as you can dissolve those things without dissolving the RNA, and then you can resuspend it in whatever you want, typically like water or some sort of buffer, some sort of safe buffer like a tris buffer or something. Often what you're doing is like a 70 to 80% ethanol wash. So the ethanol is going to dissolve the salts. The salts are really small and it's easier for them to redissolve than it is for like your RNA to redissolve, because the RNA is longer. It's got more of these interactions with one another. When it's in that precipitated out phase, it's making like a bunch of interactions with one another. We need to get it to change all of those interactions for interactions with the solvent in order to dissolve it. So there's going to be a lot more interactions that need to be made and broken than with the salts. And so we can use, by using like a 70 to 80% ethanol solution, the RNA is going to stay precipitated, but those salts and things are going to come off. Then we can air dry the pellet and redissolve it in what we want. Recently, what I've been using a lot is actually like starting with the TRIzol, but then instead of doing the chloroform, instead of adding chloroform and doing this phase extraction, they're actually kits. So I use like TRIzol kit from like Zymo. I don't work for them, or I'm not paid by them or anything, but these kits are really helpful. You can actually take that phase directly and stick it onto a column. There's lots of different column methods that you'll see in like biochemistry and molecular biology that basically take advantage of differences of the different solubilities and take advantages of the ability to precipitate out nucleic acids, get them to bind to columns, and then precipitate them off the columns. This can be easier than trying to deal with one of these pelleting methods, where it can be really hard to find your pellets and things. So these columns can be really helpful, and they also have column methods that you can use that you can take from that aqueous phase. So when you add the chloroform, you do that separation, and then you add it onto the column. Instead of doing all the spin steps like this, you would do them on a column, or instead of pelleting things out, you're getting them to stick to one of those membranes. So that's something that to consider, because you can lose a lot of yields and things during the pelleting step if you're not really careful. So that gives us the RNA, and often what we're going after is the RNA. But we can also go after the protein or the DNA that's left over. And I'll say that typically it's going to be easier if what you want is the protein. This is not the easiest way to go about it. Typically, you would only be doing this to get protein if you also needed the RNA and the DNA and you didn't have enough samples to do it from like two separate things. Because what's going to happen is, although we can precipitate out the protein, it's going to be hard to redissolve. So easier methods are going to involve various forms of lysis, where maybe you actually include nucleases to chew up the DNA and the RNA to preserving the protein. But if you want to get all three, you can do it sequentially like this. So I say sequentially because you're actually going to precipitate out the DNA next before you can even get to the protein, so that you don't precipitate out the DNA with the protein. So remember that our proteins and our DNA are going to be found in the organic phase, and some of the DNA is in the interphase. So we're going to take those two phases. So we remove that aqueous phase, and now we're dealing with this leftover organic and interphase. And now we want to separate the protein from the DNA. We can do this by taking advantage of the fact that it's going to be easier to precipitate out the DNA than it is to precipitate out the proteins under these conditions. So proteins have a lot of versatility. Proteins typically fold up so that they hide their hydrophobic parts on the inside and their hydrophilic or water-loved parts on the outside. When you have one of these chiotropic salts like guanidinium cyanide, and when you have like phenol, this is going to help denature or unfold the protein and expose those hydrophobic parts. If you didn't have the option to hang out with that like phenol chloroform, then the protein would just precipitate. But since you're giving it that option, the nonpolar parts of those molecules can kind of help shield and glob onto the nonpolar parts of the protein that you've now exposed. And this is going to leave it soluble in those liquids. As the precipitation and things are going on forward, though, you're going to be diluting those out and adding more nonpolar things that are going to help denature the protein. And now it won't have the option of a solvent that's going to be as friendly to that denatured protein, and so it will precipitate out. But first, we're going to use more mild conditions, so we add ethanol. And then later, we're going to add isopropanol for the proteins. But for the ethanol, we add the ethanol to precipitate out the DNA. It's going to work just like we talked about before, where you have the ethanol lowering the dielectric charge, and then you have the salts helping so that the salts can find the backbone, and then it'll precipitate out, and you can do the washes. And so this is going to be just like we saw with the RNA, except that here we're starting with a different, starting from a different portion, because at that negative charge of the TRIzol, the DNA is not going to be soluble in that aqueous layer, but it will be soluble in the some of it will be soluble in the organic layer, and then some of it will be in this interface, and then you're precipitating out all of it in this step by adding the ethanol. Okay, so when you precipitate out the DNA, instead of when we precipitated out this RNA, we typically just like aspirated off this liquid and got rid of it, or we saved it just in case. But we didn't do anything with it unless we couldn't find the RNA and we had to go back and like back extract or something and try to get more out of it. But when we're dealing with here, if we want the protein, we're actually going to save that liquid. But for now, we're dealing with this DNA pellet. So we take that liquid off and we set it aside for the protein later. Now we can take that pellet and we can wash it and redissolve it. And so when we're doing these washes, it's typically in like a sodium citrate ethanol solution. So you want to keep that salt in there so that the DNA is going to stay precipitated. And then you can wash it off and redissolve it. When you're redissolving it, you typically actually add like a mild base. And so remember that when we had those acidic conditions, it's going to keep the DNA precipitated. This can make it hard to redissolve. And so to help it redissolve, you can actually add a mild base in order to help deprotonate those bases, so that they'll dissolve more easily. So a note of caution is that you would never want to do this with RNA, because that could cause the RNA to break, because that 2' OH we talked about earlier, it can actually deprotonate at a high pH, and this can cause it to like break, like attack itself and break. So you wouldn't want to do that with RNA, but you might need to do that with your DNA in order to get it to dissolve. And so always look at the protocols to see the various things. Okay, so that'll give you the DNA. And now we're just left with the protein. And to precipitate out this protein, so now we're taking that liquid that was left over from the DNA precipitation, so this phenylchloroform ethanol mix. And so we have proteins in here, and now our goal is to precipitate them out. And so what we can do is we can add isopropanol. Isopropanol is going to help denature the proteins even further. It's going to be nonpolar. It's going to help disrupt the protein's interactions with itself, make it like totally unfolded, and now it doesn't like the solvent it's in anymore. It's not enough for it, and so it's going to start preferring to make bonds to itself, which means that it's going to precipitate out. And then we can wash it and redissolve it. And this now it's going to be harder. And so it can be sometimes, instead of actually like pelleting it down, you just do dialysis. So you exchange it against a solution, such as one with the detergent SDS, or you can redissolve the pellet using like an SDS solution and heat and stuff. And so it's going to be hard to redissolve those proteins because now they've made all those interactions with one another. It's going to, and so you just kind of get this clump of stuff. SDS is this detergent that we can use to help solubilize and denature proteins, and so it'll solubilize denatured proteins. So we use this when we're doing like an SDS page gel to unfold proteins, so to denature them and to actually coat them in this negative charge is one of the benefits. So you can use electricity to power it through to a positive charge, but it also helps keep things soluble because you have these negatively charged groups. But also this nonpolar tail that can kind of go up onto the hydrophobic parts, but then that positive charge keeps it so that the water still wants to hang out with it, so you get this soluble. So you can help solubilize the protein by adding SDS either to the pellet or dialyzing it against the pellet. So basically sticking it into a little pouch with SDS on the outside, and the SDS will flow in, but the protein can't flow out. And therefore you're adding SDS to your solution and hopefully therefore getting the protein to solubilize. So that is the basics of how you can get 3-in-1 out of your TRIzol extraction.